This section will be comprised of 3 shortish talks, 20 minutes each, and then the 3 panelists will be taking questions from the audience. The first speaker is Rich Zemel, who's a professor of computer science at the University of Toronto, and he's a world-renowned expert in machine learning. So, okay. Thanks.
Okay, thank you. Let's see if I get this. No, it's the pointer. Which is, oh, that was it. How do you back up? Okay, good. Well, thanks. It's great to be here. I've enjoyed the meeting a lot so far, and it's a very illustrious group of speakers and participants. So it's been a lot of fun for me. And I'm actually at the University of Toronto, so I'm bringing a perspective from north of the border down here, but the kind of issues we're talking about with data and privacy and transparency, all these things are pretty universal. Okay, so let me see which did it here. There we go. So to start off with, think about targeted advertising, and imagine that you like to vacation places, and Google just was brought up. So imagine they're giving out ads for vacation spots, and your friend got an ad for a nice looking vacation spot like this, and you didn't, and you're upset. You're wondering, why wasn't I shown this ad? Okay. And we're used to lots of automated decision making these days, things from what kind of insurance rates you're getting to whether your paper gets accepted at a meeting, or whether you get into the school of your choice, your kids get into your school of their choice. And it's getting more complicated as, for instance, like with healthcare, there's pre-screening now, looking at your online behavior to decide what kind of healthcare options are going to be offered. And so the idea is that we started with this work was, say, can we somehow make decisions in an automated fashion that respect fairness, whatever that means. Okay, so we'll try to get at a definition of what we mean by fairness in a second. And the concern with fairness is discrimination. So the population, we're going to say, includes various kinds of minorities, from based on ethnic background, or religion, medical, geographic, whatever you want to consider the minority for a particular case. And the aim is that these are going to be protected by law, some sort of public policy, or ethics. And to fit with the previous talk, if, let's say, we can't completely control our data, so the scheme is being hatched and it hasn't completely been perfected, so we aren't controlling our data. Instead, we want to regulate how it's used, which is very similar to what was discussed, but specifically with respect to decisions. That is, what decisions are being made based on our data. So it's not necessarily just what the access is to the data or what they can see about us, but how decisions are made based on that data. Okay? So that's the focus of what I'm going to be talking about. And the kinds of things to worry about are cases like this, where, for example, with credit card companies, the Capital One can use some tracking company that looks at users' online behavior, and based on that, in their search history, various things that they do, decide what kind of credit card rate and annual fees and interest percentages that they're going to have to pay. For different users, they're going to get different offers. And so minorities may get steered into higher rates. And then historically, there was something called redlining, where, so this is a map of Philadelphia from the 50s. And the red regions were regions where it was hard to get loans or mortgages for people who lived in those regions. And those were typically kind of low-income black regions, but they also included some middle-income regions for that group, and didn't include some low-income white regions. All right? So when you take into account geographic area, then you can deny service based on this kind of thing, and it leads to discrimination. And as I said, the landscape's changing these days with automated decisions. So when decisions are made based on things like online behavior and based on a data set that can be collected in the past, and the worry is that the decisions that were made in the past are going to be perpetuated in the future. And so whatever biases were there are going to be persistent in the future. And the responsibility of the machine learning algorithm that's actually going to be making that decision has been largely ignored. Right? So an example here is you're looking for employees for a call center, and the learning algorithm finds that the optimal employee lives near the job, has a reliable transportation, and uses 1 to 4 social networks. Right? And this was an article in Slashdot, and they said that, and you can read it, practices that even unintentionally filter out older or minority applicants can be illegal under federal equal opportunity laws. If a hiring practice is challenged as discriminatory in court, the company must show the criteria it's used or proven to predict success in the job. Right? So this is one example. Another one is in lending decisions. So that was another one I was mentioning with banks. And this was an article in the New York Times last year about banking startups using tools for lending. And so this one says, for regulators that are enforcing anti-discrimination laws, applying the modern techniques raises problems. So you can't, by law, discriminate against applicants on the basis of race, religion, et cetera. But big data lending relies on software algorithms working on their own and learning as they go. So with so much data and so much complexity, an automated system is in control, and software could end up discriminating without being programmed to do so. Okay? So that's the concern here. Is there a way that we can regulate it, okay, to fit with the previous theme? Is there a way to kind of insert some regulation into this wild, wild west of automated decisions? Right? And so we've been working on this for a few years now, together with Cynthia and several other collaborators for the last few years, working on a general framework of what we call fairness. And the basic idea has this flavor. So you start off with a representation of an individual, so call that X. That's the data, the demographic data, whatever data including search history, whatever data you have about an individual. And some vendor, let's say an advertiser, wants to decide, will I show the ad to that person or not? And that decision we'll call Y. Okay, a yes or no decision, is that person going to get the ad or not? And so you can imagine you try to build a fair decision maker or a fair classifier by just looking at the decision Y with respect to X and say we want somehow the decisions to be fair. So our main idea isn't to focus on the decisions necessarily, but to insert an intermediate representation Z here. And the idea in Z is that we're going to have an intermediate representation that will be delivered to the vendor, and the vendor can use that intermediate representation to make its decisions Y as to whether or not they're going to show the ad to that person or not. Okay? So that's the key idea, is that there's this intermediate step where you take the original data, convert it to some new representation, and that's in the purview of society. That's society's responsibility, is coming up with and regulating that representation Z as a function of X. On the other hand, going from Z to Y, the vendor can do whatever they want. Okay, they're trying to do what they would maximize whatever their utility is in that case. Okay? And this is this basic idea of inserting this intermediate representation is the kind of key idea. I won't get into all the details of it today, but that's kind of the main takeaway I want you to have from the talk, is that you can try to enforce fairness by looking at this intermediate representation and trying to ensure the fairness of that intermediate representation. And this fits with the main idea in machine learning these days, like with the deep learning revolution, is that it's all about representations, right? So lots and lots of data gives us better and better representations. And so you have these deep networks that are constructing representations. And it's often all the innovation comes in kind of crafting good representations. So in this case, we're trying to craft a good representation that fits with society's ideas of fairness. And so to keep things simple, we're going to imagine that we have two groups. So there's a group distinguished by some variable S, and S equals 1 is the kind of group that could be discriminated against, and S equals 0 is the majority. All right? So you can divide the original people into these two different groups, S equals 1 and S equals 0. And we want to be fair with respect to that distinction. And obviously, there could be one variable, but typically there'll be many different variables. Just for the sake of simplicity, we'll focus on there being one. And so what you could imagine doing is that you just throw away that bit. Does that person, what's the gender of that person? So you want to be fair with respect to gender, so you just take that out of the input. But we know that that's not feasible as a solution because there's lots of other aspects of the input that encode information about gender or whatever S might be. Okay, so it's not as simple as just throwing out that bit. Okay? So this is our overview, is that our aims, like I said, our aims is society is doing this first step. And so the aim for the society is to do two things. And this is the way we've formulated the problem. Many other people have been also tackling this problem in the last few years, including some good posters last night. All right, so our particular take on this is that we want to enforce what we call group fairness or statistical parity, which means that Z, that is the representation of the individual that we're giving to the vendor, shouldn't have any information about S in it. So you shouldn't be, but if I give you Z, you shouldn't be able to determine is the person male or female. Okay, so you want to lose the sensitive information. Right? At the same time, we want to preserve whatever the rest of the information is about the input so that the vendor can take Z and maximize their utility. Right? If you kind of remove all the information, then it's useless to Google, who wants to do their targeted ads. So you want to preserve as much information as you can while losing the information about S. Okay, so that's the key idea in our formulation. And in more technical terms, you can think of it as you want to maximize mutual information between Z and Y, minimize mutual information between Z and S. Okay? A number of experiments we did to explore and validate this on various data sets. And these are data sets that are public in the machine learning repository. And so we took these standard data sets and kind of tailored them so that they were for this fairness application, where the idea would be, typically in these things you want to just classify. Here's some historical data. You're going to take a portion of the data and learn on it and test on the remainder. And the test would be, for example, here's a new individual. Was that individual a good or bad credit risk? So you learn something on the subset that's the training, and on the test set, you predict whether they were a good or bad credit risk, and you see how well your predictor does. Okay? So that's that's the vendor's utility, to do the best possible job at predicting the credit risk of an individual. With the fairness criteria, it says, well, we want to do that subject to losing information about, in this case, age. So we choose the variable age and say we want to be fair with respect to age. Okay? Another data set, the adult income data set, we want to predict, in this case, the vendor is trying to predict whether or not the annual income is bigger than $50,000 or not, and the sensitive feature we chose was gender. There's also a health data set, which is a prime kind of focus of data for this fairness application, because there's a lot of, like I said at the beginning, there's a lot of kind of pre-screening that goes on in health, and you want to be sure that you're fair with respect to various criteria in the population. In this case, we were just going to take a data set that existed online, a fairly large data set with 150,000 instances, and try to predict whether or not the patient was going to be hospitalized. That was what the vendor was going to predict. Obviously, that could be of practical use when they're trying to make decisions about what kind of health care to offer them. And the sensitive feature, in this case, was age. And so without going into details, I just want you to focus on a couple things. The main idea is, on the far left is the accuracy if you don't include fairness. So you'd have just a standard predictor, a machine learning predictor. This is on a test set, you get around 70% in this yellow bar. But there is some discrimination. So this is saying how much discrimination is there at the output with respect to the group that we're trying to be sensitive to. In this case, it was age. In this case, it was gender. And here it was age. And you can see that the yellow bar is without any fairness criteria. When we put our fairness criteria, that's the blue bar over here, we lose a little bit typically in accuracy of predictions, but we also completely eliminate, in most cases, or almost eliminate completely, discrimination. Okay, so that's the aim here, is to lose very little in accuracy, but try to gain in fairness, in this case measured in discrimination. And we can do this in a deep network, train a neural network without any fairness criteria. And again, you get some loss in accuracy when you include a fairness criteria, which we call MMD, but you gain a lot in terms of removing discrimination. And then now trying to visualize what's happening to this idea that we're losing information. One way to do that is to take the Z's and project them down to 2 dimensions and color them now by the S values. So the blue ones are S equals 0 values. These are the individuals where S equals 0. Their representation in their Z representation projected down to 2 dimensions. And the reds are the S equals 1. And you can see that they're fairly separate, and this is the case without any fairness criteria. When we include our fairness criteria that's supposed to be removing information about S, you see that they're all jumbled together. So that if a vendor gets an individual, a representation of an individual, which would be one of these points, just by looking at that, it can't say, well, it's, that person is young or old, or male or female, right? They couldn't tell what S was by looking at this, whereas in this case they could. Okay? So I'm always on a quest for new data sets. So these data sets are somewhat old, and we've tried lots of different, so recently we've been looking at lots of different data sets. So recommender systems is a prime example where you might want to do this. Other data sets are things like, so Facebook data set, we've worked on that some. So a recent one I'm excited about is called Vote Compass. And this is a kind of political polling or surveying data set. And it's a website that surveys people based on their political beliefs. And in the end, it tells them what political party their views align most closely with. And asks a bunch of questions. So questions could be things like this. National budget deficit should be reduced, even if it means fewer public services. Funding of schools, funding of universities, those kinds of questions. And people have to say, how strong, whether they agree or disagree on a scale of 1 to 5, and how strongly they might feel about that issue. And so we find that this is very interesting data because you also have all the demographic data about these people, as well as their party affiliations, all right? And so then the idea is that imagine now some vendor has access to this data and wants to advertise. So some political party may want to say, okay, we want to advertise to all the people who our views are aligned with our party, but we want to do this in a way that now society has to step in and regulate and say we want to do this in a way that doesn't discriminate based on religion, okay? So we've been looking at this. And so if you're going to target ads to this political group, then without some bias, let's say for religion. So in this case, you can see that what this is just showing is that you get clustering. So this is from the Australian national election in 2013. We have about 1 million respondents in our data set for this. And so it's a really good data set. And there were 3 different parties, the Liberals, Conservatives, and Greens, red, green, and blue here. And so there's fairly strong clusters. And now we're working, and I'm not going to show you, but it's the same type of idea, which is we want to be fair with respect to religion and find that we remove information about religion, and we're able to still do a good job of estimating whether or not somebody's favorable to, whether their views are favorable to one party or another. Okay? Okay. So, yeah, so I'll just wrap up now. So the main idea I want you to take away from this is that you can't leave it all up to the machine learning algorithm, that we have to specify, we as society has to specify some sort of aims or criteria that we want, and that there's this inherent trade-off between society's aims of avoiding bias, so that's kind of the public good that Butler talked about in the last talk, versus the decision accuracy. That's kind of what the vendor wants to do, is be as accurate as possible as to whether that person is going to be favorable to the ad. And then what can we do about this on an individual basis is a question. And there's like a cautionary tale. So there was an interesting article, I just threw this slide in last night, because there was an article yesterday, I don't know if people saw it, about Facebook, saying that former Facebook workers said that they routinely suppressed conservative news. And so I just took an excerpt from the article, which said that they prioritized stories that were shown in the trending section. And this is really important. So 167 million people in the US look at news. I mean, those are Facebook users, and a lot of them are reading news on Facebook. And the workers prevented stories about right-wing, various right-wing things and conservative topics. And they were instructed to artificially inject stories into this trending section. Right? So the main point here is that, so this is a case where no matter what you do, even if the algorithm's biased, you still have to be watchful that, that a human doesn't insert bias afterwards. Okay? So that was kind of interesting. So the bottom line for this work is that we're trying to come up with a notion of fairness that is workable, and that depends on working with legal scholars and public policy experts. And the aim that we have so far, like I said, is this statistical parity or quotas. But obviously that's a first step, and we need to do some further work to help refine and come up with the objective. Thank you.
Thank you. The next speaker is Dan Ford. He's a Chief Information Security Officer at Silent Circle. He teaches at Capital Technology University on topics of both security and crypto, and he's going to give us an exciting walk through the Apple versus FBI issue. Thank you.
Sure. Good morning. So actually, I'm the former Chief Information Security Officer at Silent Circle, so I'm no longer there. Jon and many of you may have known Jon Callas, but Jon and I both left about a month or so ago. So anyway, I'm going to be talking a little bit about iOS security and privacy in smartphones. While I am somewhat biased in this in that I use an Android phone, but I also use Apple products all the time. I use all of them. I probably have about 100 mobile devices in my home lab, and I'm constantly looking at these things all the time because, well, security changes over time, privacy changes over time, and I want to know what all the latest trends are. And I'm frequently asked, Dan, what is the most secure operating system out there? What's the most secure firewall? What's the most secure smartphone? And my answer is pretty much always the same, in that the most secure system is the one I'm currently not trying to get into. Because if I want to get into your system, I'm going to get in. If a bad actor wants to get in, they're going to. And primarily, this is because they have more time, they have more resources, and you don't know you're being attacked. And I thought about this not too long ago, and I realized that my parents were much smarter than I ever gave them credit for growing up. And I learned a lot of my security lessons about examples growing up, and one of them comes down to what is the motivation of this persistent hacker? And I had this dog. It was a Siberian Husky. And we had an invisible fence. And every day, I watched this dog go to the boundary, because if you're not familiar with the invisible fence, there's a wire underneath, and it's got this basically, it'll shock him with a 9-volt battery. That doesn't hurt very much. But when you get close to the boundary, it would beep. And this Husky, every day, would go and check to see if it was still active. And sometimes it was, sometimes it wasn't. And sometimes it wasn't was because the environment changed. It was really rainy, and so that interfered sometimes. It was snowed a lot, so it interfered. And then sometimes there was just a rabbit, and it didn't care, and it would just take off and run and get through, and then it would sit outside on the other side of the boundary and wait and bark and howl until we came over, took the collar off, and brought it back in. Well, that is, to me, the definition of an advanced persistent threat, because they're always going to do it. They're persistent in this nature. So while I am an Android fan, I'm also an Apple fan, and I believe that out of the box, Apple makes the most secure and private smartphone on the market for the general consumer. They have put more thought, I believe, than any other vendor out there in terms of making a device. They've incorporated, system security, which deals with encryption. It deals with keys. It deals with how and why any type of code should be authorized to execute on that system. And of course, there's encryption. There's various types of encryption that's going on here in terms of public key, data at rest, data in transit. Data protection is heavily used, and it's tied to your passcode. So a lot of the security goes completely away if you don't put a password on your phone. Even if you have a 1-character password, while it's easily guessable, you still get a lot of these security features. I would never recommend putting 1 character on. I say it's not whether or not you're paranoid or not, it's whether or not you're paranoid enough, and I still use well over a 10-character password to get onto my phone. But I also like phones that have fingerprint scanners because this way I can have that phone. And if I feel insecure, I just reboot my phone because then I have to put in my extremely long password. Some of the core around Apple security is their application security, because they have implemented checking at not only install time, but also at runtime. So every time I enable an app on there, I go to click on that application, Apple is working behind the scenes on this device to validate that this is authorized code. And they do this through many different ways. They utilize what's called address space layout randomization. They utilize kernel address space layout randomization. There are sandboxing systems on there to make it difficult for an unauthorized actor to gain access to your data. They've implemented network security. So all the latest things in terms of data in transit. They have VPNs. They're enforcing TLS security. And now they've just made it so that any new app that utilizes communications is going to have to be IPv6 compliant, because IPv6 has some enhancements to security over the traditional IPv4 that we are all familiar with. And then they've enabled some things for privacy. Now, this is out of the box, that these things are there, but not all of it are we familiar with how to enable. And hopefully you'll get some of that from here and just some quick tips on what you can do. But here's another view. Here's an architectural view as to what Apple has done in order to provide this level of security. And I want you to pay very close attention to the very bottom, because we're going to get into this towards the end of the presentation, because this is the key part as to what I believe as to why it is very challenging for law enforcement to just have an exploit for just one device, or to go to Apple and say, hey, we just want you to do something, but just for this one device. It makes it very challenging, and we'll get into that. But the great part about Apple, and this one architectural diagram to me kind of brings it home for Apple, and that it is a great combination of software and hardware and services that are all working together almost simultaneously in order to provide you a secure and private product. I don't believe that there's any other product on the market today that is working like this in order to be able to provide you this experience, all at the same time of being a device that seems to be a status symbol. And even for people like myself that's an Android fan, I'm not giving away my iPad, because I believe that iPad is just fabulous. So as an Android person, I'm using an iPad. I use a Mac. I still have iPhones. My kids have an iPhone, mainly because he wanted something that had the fingerprint scanner, and he understands that a long password is going to be much more secure than a small password, and he's 15. So if Apple's able to provide this, it makes it to where we can raise the security and privacy of an entire population group significantly over time, just by them doing these things for us, by adding a strong password. And a strong password could be as much right now as 8 characters. You can't really say that on many other devices. And the reason for that is because of what Apple has implemented. So separate the aspect of your screen lock, what you're seeing when you just have the device right here, the screen lock. This is different. We're going to call this being an online attack. So this aspect of an online attack means the attacker has to guess and keep putting in numbers. So Apple has delays. If you put that in there and configure it, they have delays that will make it to where after so many attempts, it'll take you an hour to try to do that. And if you do it so many times, it'll just erase your data. But then there's the offline attack, which is the part that is a little bit more challenging. There is no such thing as failed attempts. The device is off. We're attacking it when it has not fully booted up. And Apple, in their ingenious, has implemented delays in the hardware. So after every failed attempt, they've added artificially an 80 millisecond delay. So now a 4-character password, or rather 4 numbers, will take approximately, I think if my math is right, around 12 minutes, something along those lines for a 4-digit PIN. Now you take that out to a 6-character set, and we're talking years to go through all those combinations. An 8-character set, I think the Earth is gone. I think it's something like a couple million years or something like that. So they've added those artificial delays, but that's a brute force. And the brute force is we're trying one combination at a time until eventually we're in. Well, that's not necessarily really realistic to only try it on one device. But Apple's at least done this in order to make it difficult if you lose your device for someone that's not authorized to get access to this data. So some of the things that you still kind of need to do to increase the security and privacy of the product that Apple's already provided, that while they do a great job right out of the box, there's still some things that you should do, such as go into your password settings and make it to where after X amount of failed attempts, which I believe the default is 10, that it will erase your data. And this is so in the event that you lose your device, the data's gone. When you're on a Wi-Fi, because no matter, even if you've done all these things, there's still so many things that these mobile devices are giving off that you have probably no idea about because you're connecting to the cellular network. So you have all of these unique identifiers that allow someone malicious to still track you. If you have that Wi-Fi access on and you're not connected to a Wi-Fi access point, you're broadcasting out every SSID that you have ever connected to. And for someone like me, that's great because I can put up an evil access point and start forcing you to connect to me. So if you're not using your Wi-Fi, turn it off. If you're not using your Bluetooth, turn it off. It's no different than your car. If you don't want someone stealing your car, when you take the keys with you. You turn off your car, you lock the door, and then you go. Otherwise, if you leave your car on, well, someone's going to steal it. If you leave your Wi-Fi on, someone can steal your data. Apple's not going to protect you against that. They say, well, turn off your Wi-Fi, turn off your Bluetooth. But you should also disable things such as geotagging in your photos. You never know where that photo is going to go. And there's data in there that allows someone to track you. And that's can be extremely, we'll say it can be extremely frightening in the event that someone decides to show up at your house because you cut them off on 495 and you just so happen to have your Wi-Fi on and I'm good enough to where I can track you and that MAC address pretty much indefinitely. Some of the things you should also do with your iPhone and your iPad. Wipe the keyboard cache. A lot of people don't think about that, but your keyboard cache has a certain amount of characters, and most likely, if you're mobile banking, I can get your password from your keyboard cache. So wipe it. You should also look to enable things such as validating that all of your email is utilizing SSL, because you want that to be encrypted. If it's not encrypted, and not all email providers force you to have to use encryption, which I'm still surprised today that this is the case, because encryption should be a standard. I mean, even Google is encrypting your search strings so the provider doesn't know it, because that's proprietary to them. They don't want everyone to know what you're searching for. So they encrypt. When you go to Google now, google.com, it's SSL enabled. So why isn't everything SSL enabled at this point? I don't know the answer to that. I'm still trying to figure that one out because even the banks have recently updated all of their web security to go to TLS 1.2. 18 months ago, this was not the case. Many of them were still on SSL version 3. And so how many vulnerabilities are in that? So this slide is current as of March 2016, and most of this data came from a website called CVE Details. It's a website that we use to find very easily a lot of vulnerabilities. And this might be confusing to some of you. You might be wondering, how could I say that Apple is such a secure device when they have all these vulnerabilities? They have more vulnerabilities than Android, but yet we keep saying that Android's not very secure. We say that Microsoft doesn't make a secure product, yet Apple iOS has more vulnerabilities than, well, it looks like to me, Windows 8 and Windows 7 and Windows XP combined. Probably even if we added Windows 10 in there. Some of this has to do with the criticality levels of the vulnerabilities. But one of the things that I believe that Apple does probably better than, certainly than any smartphone vendor out there, is they provide a patch to all of these vulnerabilities all the time. They are conscious of these. They are very forthright. They are open. They say, yep, here are all the vulnerabilities. They detail them out in their release notes, roughly every quarter, sometimes they're monthly. And they tell you, these are all the vulnerabilities that we fixed in this patch. And then they notify you all the time. Sometimes it's annoying. In that, hey, you've got an update available. You've got an update available. Because they want you to update. If you patch your system, the likelihood for a malicious actor to exploit that system goes way down because they have patched it. Android doesn't necessarily do as good of a job because it is dependent upon all of the smartphone vendors that exist. And the only one that was patching extremely fast happened to be Silent Circle with BlackPhone, because that was one of the things that I was mandatory about, that we would patch any significant vulnerability in less than 72 hours. Because we had to, because Android's vulnerabilities tend to be much more devastating when one is found because of all of the capabilities that a user has. Android has multiple app stores that you can go to. You don't just have to go to Google Play. You can go to F-Droid, Amazon, and all those checks go away. With Apple, you must stay within the Apple ecosystem unless you jailbreak it, in which we'll talk about jailbreaking here momentarily, like now. So again, we'll go back real very quickly, look at the amount of vulnerabilities that exist in Apple. And we're going to focus on Apple for a moment because, as I said, Apple is probably, in my opinion, the most secure smartphone that exists. Security depreciates faster than taking your new car off the car lot. Over time, that new car's value over 5 years decreases by 66%. Well, in mobile, we work even faster. We know that mobile devices and mobile operating systems change every 3 months because if you've got 500 some vulnerabilities over the last couple of years, you've got to patch them, you've got to fix them. So you have a really secure system, but within in iOS 7, within 66 days, the security in iOS 7 made it so that basically anyone could get in, because the average time that a release for iOS 7 hit the market and then a jailbreak occurred was 66 days. For iOS 8, it's 18 days. Now, I'm not quite sure as of yet as to why some of these dates vary. I believe that some of this has to do with new hardware being introduced to the market at the same time of a new iOS, and then the hacker community or the research community, or there's really no difference, the jailbreak community, has to reverse engineer all of those things that Apple has done in order to make that secure product. They've got to go through the system security, and how are they going to get out of the sandbox? How are they going to break ASLR? How are they going to break kernel ASLR? How are they going to break the code signing at install time and at runtime? How are they going to break DEP? All of those things have to occur in order to be able to create a jailbreak, an exploit that can be remote executable, an exploit that can actually get data off a device, no matter if your password was 6 characters, 4 characters, or 12 characters. In iOS 9, we have increased again back to 81 days. Some of this has to do with, my guess again, because iOS 7, when it was released, we also had the release of a new phone. With iOS 9, we had the release of a new phone. So I believe the phone, of course, with the new hardware and how fast they are, makes the jailbreaking community take a little bit longer. There are rumors that there's already a jailbreak that exists for iOS 9.2, but it hasn't been released yet. They've only been talking about it, and they put pictures up on YouTube and Twitter, and they want you to follow them. I have no reason to believe that a jailbreak doesn't exist. The reason why they're not putting it out is they're probably waiting for 9.4, because they want that jailbreak to exist longer. And so if you time it with the release of the next iOS version update, that means your vulnerability exists longer in the market. And the longer a vulnerability exists, the more often and the more times that you can use that to exploit something. So hopefully I can get this down in the next couple of minutes. But really, to me, we hear about Apple and the FBI, and there is no difference between anti-theft. In this case, if you're making something that is going to be anti-theft, it is also anti-law enforcement. You cannot separate those two mechanisms. If I don't want an unauthorized actor having access to my data, I have to create a system that is anti-theft. There is no difference between the jailbreak community and forensics. If I'm going to create something and allow jailbreaks, those same exploits that are being used to do a jailbreak are also the same exploits that are being used in forensics and law enforcement investigations. And if we happen in this country decide through the court system to permit law enforcement to force a vendor to enable and exploit a system, so too will other countries. It's not that whatever we do here will be affected globally. So hopefully I'll wrap this up very quickly. That last piece, the Apple UID, which is a device key, it is unique to every device. Apple does not know this key. That is crucial to their security. They're burning this directly into the silicon, directly into the chipset. They don't know it. And then it's sealed off to where no device, no software, no firmware can read it, not even Apple. And then there's a GID, which is the group ID, which is tied to a series of processors. That one's known. Apple also has a root CA public key on there. That's what says this is what we're going to use in order to be able to validate that only code from Apple is going to run. So the question is, can Apple write code that's only going to exploit one device? No, not without an exploit. They would have to do everything that the jailbreak community is doing and those malicious actors because of that UID. That is unique to that device. Apple doesn't know it, and as such, no one else does either. And so if they were to write an exploit based on what law enforcement wants, it doesn't affect one device. It affects all of them, not just here, but globally. Thank you.
Thanks. So our next speaker is Cynthia Twerk. She's on the move now from Microsoft to Harvard University. She's the leader of the differential privacy field. She has won the Dijkstra Award. She's the member of the National Academy of Sciences, National Academy of Engineering, Fellow of the American Academy of Arts and Science, and a newly minted member of the American Philosophical Society. And all these awards are truly justified. So please, Cynthia.
Thank you, Tom. Okay. So, Butler was talking today about the ability to control one's data, and through claiming also the ability to control the use of one's data. And I'll just point out something which is pretty obvious. The approach empowers me to limit the use of my data prospectively, obviously not retrospectively. It's been used. What can you do about it? Well, what would we want to do if we want to limit the use of our raw data in the future? One thing is the ability to limit the use of the future use of our raw data would address some of the frustrations expressed by David Mazuris and Eddie Kohler. We have, in general, though, a pretty good intuition of some of the things that we might mean by limiting the future use of raw data. For example, I've allowed my blood to be drawn for use in medical studies. And I may say at a certain point, I don't want you to use my blood. I don't want you to use any of the data that you got from measuring my blood for your future studies. I might have been a member of LinkedIn, and I might say, okay, that's it, and I don't want you to show my data to any of your future, or any of your subscribers from now on. Same thing with Facebook. I might want protection from targeted ads. Do not use my data for targeting ads. Give me the general common offering. And something maybe even as controversial as the right to be forgotten, and I'm not taking sides on this, but I don't want maybe Google to report on my past. And this is very topical now in France. Okay. So there's a fairly natural intuition for what it means to limit the future use of raw data. But what about data products? That is to say, things that have been created by combining the data of many different people, so entangled data. So for example, through the miracles of machine learning, my moving watching history will affect what movies are recommended to you. Similarly, what I click on when I search will affect the order of search hits on similar queries that are presented to you. You make a similar query, and you get an ordering of possible results that's affected by my behavior in the past. My data could also be reflected in published statistical summaries and conclusions. So the question that I'm asking is, what can limiting the future use of my data possibly even mean in this entangled setting? So in this, one thing that you could say is, okay, for all of those things, I want you to recompute all of them now without me. So this is clearly a non-starter. It's wildly expensive, and it's a great vector for a denial of service attack. We all just start telling Netflix to recompute and recompute and recompute, and we tell Google recompute and so on. Okay. It's also a source of privacy compromise. Even if you could do this, it's a source of privacy compromise. Why? Well, here are the statistics that include my data. Here's some data set, and the number of people in the data set that have the sickle cell trait is 33. And now I ask you to recompute this without my data, and lo and behold, you now publish that the number of people in the data set that have the sickle cell trait is 32. So it's clear what my sickle cell status is. So I'm, in this brief presentation, going to present differential privacy as a solution concept to what it could mean to reduce my influence in future, of my data in data products. So differential privacy is a definition of privacy that's tailored to statistical analysis of big data. It was co-invented with McSherry, Nissim, and Smith. And I'm going to suggest that it's sort of morally close to or nearly equivalent to not having had one's data used in the first place. And so intuitively, if your data haven't really been used in the first place, you could sort of say you have implemented the right to be forgotten. It also, differential privacy also will safeguard privacy even under recomputation were we to go that wildly expensive route. Okay, so to motivate the definition, suppose we have a data set that is filled with interesting and sensitive information about individuals. And I have a picture here of the philosopher Helen Nissenbaum, who has written extensively on privacy. And we want to come up with a notion of privacy that permits a data analyst to learn interesting things about the data set as a whole without learning anything that is compromising the privacy of the individual members of the data set, such as Nissenbaum. So what could the notion of privacy possibly be? And the first thing that everybody tries is, well, the data analyst shouldn't learn anything new about Nissenbaum. And there are a lot of good reasons for trying this kind of definition. In interest of time, we won't go into those. The problem with this approach, though, is that if this is your definition of privacy in statistical data analysis, then what in fact is the point of your data set? So to illustrate this, suppose I'm from Mars and I erroneously believe that all humans have 2 left feet. And in particular, I believe that Nissenbaum has 2 left feet. And I find that by studying the statistics of this data set, the overwhelming majority of humans have 1 left foot and 1 right foot. So now my beliefs about Nissenbaum have changed. I have learned something new about her. Now, was her privacy compromised? So we would argue no. And in fact, we would have learned the same thing had Nissenbaum's data been replaced by some other random member of the population. This is Latonya Sweeney. Okay, so this is a stability notion. It says if the data set doesn't change very much, you'll probably learn the same things, or you'll learn the same things with the same, almost the same distribution. So stability preserves privacy. But just to give you some intuition, like I'm saying the same thing should be learnable even if we swap out a couple of people and maybe replace some people. Why is any kind of real learning consistent with that at all? And again, we don't have time to go into it, but this notion of stability is essential to generalizability, to being able, from looking at your data set, to actually generalize to the population as from which the data were drawn in the first place. And generalizability is, of course, crucial in machine learning. You don't want to overfit to your actual data set. You want to learn about the population that you were drawn, that the data were drawn from. So the point is that privacy and generalizability are completely aligned. And that gives you maybe a tiny bit of intuition about why you can achieve the 2 of them simultaneously and actually learn important things about your data set and your population. So in English, differential privacy says that the outcome of any analysis is essentially equally likely independent of whether any individual joins or refrains from joining the data set. So that means that, say, you learn essentially the same things with the same probabilities, almost the same probabilities. If Nissenbaum's data are deleted, Sweeney's data are added, Nissenbaum's data are replaced by Sweeney, and so on. So in this sense, it's sort of nearly equivalent or morally equivalent to not having had your data used in the first place. So when Butler talked about aggregating for the purposes of privacy, you could imagine that you would use differential privacy and you would actually really have the privacy and also not have anybody's outcome be too heavily influential. Formally, and this is the one technical slide, to understand this, we have to have a notion of a pair of adjacent data sets. So 2 data sets are adjacent if basically they differ in the data of just one person, as I've been explaining with Nissenbaum and Sweeney. And we have algorithms that, for historical reasons, are called mechanisms M, and they operate on data sets. And the algorithm is randomized. It introduces carefully calibrated randomness at certain points in the computation. And we say that the algorithm, or the mechanism M, gives epsilon differential privacy, and here epsilon is a parameter that gets set by whoever is handling or controlling the data, or perhaps by society. If for all pairs of adjacent data sets, X and Y, in every possible event S, the probability that we see this event is essentially unchanged when the data set is X or its neighbor Y. So the probability of seeing this event S is at most, when the data set is X, is at most, let's say, 1 plus epsilon times the probability of seeing this event when the data set is Y. So as epsilon goes to 0, we get equality. And X and Y are completely symmetric in my definition, so we have the other inequality as well. And the key point is that the randomness is the randomness that is introduced by the algorithm, by the mechanism. And so it holds for all data sets. The key properties of differential privacy are, first of all, that it's immune to all current and even future side information. So if you've operated on a data set in a differentially private way and released a result, then no matter what anybody learns in the future or how much they from other sources of data, voter registration rolls and IMDb and things like that, it's impossible to sort of extract any more information from the data release. So it's immune to the famous linkage attacks as in the Netflix data, what was it, the prize, the Netflix competition for improving the search engine rankings. It automatically yields group privacy, although the parameter deteriorates as the size of the group increases. And that, of course, makes sense. If you change the data set substantially, then you should get different outcomes. If you replace all the Republicans with Democrats, for example, you should get a different outcome. Really importantly, we can understand the cumulative loss under multiple computations. And that's tremendously important. This also lets us follow the recomputation approach. Because we understand how privacy loss accumulates under recomputation, we can scale the privacy parameter to compensate. The reason that understanding the behavior under composition or multiple computations is so important is that it makes differential privacy programmable. So think about ordinary algorithm design. In ordinary algorithm design, we know that addition and multiplication are a basis for all of computation. But that's not how people program. What they do is they develop various computational primitives, and then they use ingenuity and a lot of thought to design more complex algorithms that carry out complex tasks by combining these computational primitives in the right way. And differential privacy is similar. We define a couple of differentially private building blocks, and then we use the composition theorems to combine these in interesting and creative ways to get differentially private algorithms for more complex computational tasks. So that's where it gets all of its power. And there's a very rich algorithmic literature about differentially private methods to carry out many different kinds of tasks. And there's also a book on the algorithmic foundations. So as I said, differential privacy introduces some randomness, some distortions at various points in the computation. And you could think in analogy to Impressionist art. You have the reality, which is very, very detailed, and you have the slightly blurry version. And the question I want to ask is, which is right? Which one is really telling you what's going on? So the Impressionists would argue that perhaps the art is telling you what's really going on. And here's one sense, technically, in which that's in fact the right conclusion. We've already mentioned that the stability guarantee preserves privacy and prevents overfitting. We've recently discovered, in joint work with Feldman, Hart, Patasi, Reingold, and Roth, that differential privacy also protects against an important source of false discovery, which is the overfitting that is caused by adaptivity or exploratory data analysis. This is when the 20th question that the analyst asks depends on the answers to the first 19 questions, or the 5th study that's done on this really important corpus of medical data depends on conclusions and questions that were raised in the first couple of studies. And, good, okay. I have to mention, of course, that it's not a panacea. First of all, there's a host of results that teach us a fundamental law of information recovery, which is that overly accurate answers to too many statistical queries is blatantly non-private. There are also policy questions. So epsilon, our privacy parameter, is sort of a nexus of policy and technology. People have to figure out how these epsilons should be chosen, what should be the cumulative loss that we permit, who gets what. Now, this has been viewed as a strong argument against differential privacy. People don't know how to set epsilon. We'll argue that no, we're actually giving you an option. We're giving you some power that doesn't exist in any other technology, which is the ability to scale things so that you can, in fact, program in this privacy-preserving way. So it's a strength, we say, not a weakness. Okay, thank you.
Okay, so we will move now to the question section. So I see that people are lining up. I wrote some questions until you guys. Okay, go.
Mark Hill, University of Wisconsin. So I have a question for Dan. So you convincingly argued that Apple couldn't break into that phone for one phone, it had to be every phone. But what if we want to trade off the right to privacy with the right to not be blown up and require access to phones under certain procedures, search warrants, et cetera? What is the technology for enabling that?
I believe it would be extremely, I would say, difficult for any, I'll put it back a different way. I don't believe that our policy should ever force any vendor to have to go against trying to protect against anti-theft. I believe that since we have seen that vulnerabilities will occur over time, we saw that any jailbreak which has to do with vulnerabilities is going to happen. We know that at least from what's been publicly made in the case with the FBI, that they went to a forensics company which utilized more than likely vulnerabilities that they found on their own or that already existed in the jailbreak community, that they will still be able to get that data. You can't separate from the math of anti-theft, and it's automatically going to be anti-law enforcement. So in order to do that, I don't believe that there's a mathematical way in which we could actually do that.
So we couldn't require those secret keys to be held in escrow somewhere?
No, it's not when you're doing it in the silicon like this. There's been arguments, while I'm not a cryptographer, the cryptographers have argued that the escrow policy just doesn't work. And even General Hayden has argued against that capability because if that is there is no such thing as a back door. It's always going to be a front door. Having that access to where we know that it is possible, I can take a look at any vulnerability for any operating system, and I'll be able to write an exploit for that. That key in escrow means that I have an additional method to get into that system, and the mathematical probability for me getting in just skyrocketed.
So, Moshe Vardi for Barais, I'd like to know what the panel thinks of the Butler's proposal for the privacy scheme.
I didn't
happy to-
understand the question.
Butler's proposal. Okay, is this on? All right. So I think Butler's proposal is really, really interesting. I think that it will provide a blueprint for research that could have decades of PhD theses. And the question that I wanted to ask, and I didn't get time to ask, was, suppose we decide we love it. How do we get from here to there? What gets mobilized first? Who starts building what? How do the policy people get pulled on board? How do what makes it, what turns it from an idea like this into a reality? I mean, I've struggled with this in other areas. It's quite difficult. So, but I think it's an extremely intriguing proposal.
Yeah, is this on? So I also felt it was very interesting, and I felt a little bit the same, and also that the key is, as some of the questions brought up, what is the 7+2? What are the kind of representations of the data that's small enough that people can understand it, and also the policies. You know, can you craft a set of policies that are understandable to a group of people? And I fear that it will go, like he said, most people want to understand, no matter what you do, understand they'll go back to defaults. It'll come back to where things are today, which maybe isn't so bad. Because then there are the people who do care will have the option of enforcing privacy and kind of, you know, their data being handled the way they are. So I think it's a great idea, but it's all about fleshing it out in some realistic, understandable way.
Yeah, I agree with Rich here in this, that even if the capability exists, the majority of the population doesn't implement it. I mean, we can take a look at this with other technologies today. I mean, the reason why cybercrime and malware continues to rise is because people just don't patch their system. It's available, but the average person, the average enterprise goes roughly 183 days before they patch, and that's why these things continue to exist. I think the same thing is going to happen with privacy. We already have these capabilities in a lot of ways on how to, how to become more private. We just don't enable them. We don't use them.
Okay. This question is for Rich. I'm Mike Hicks from University of Maryland. So I'm curious, when you showed the correlation and you used age as the discriminator, I first thought, well, what if age actually is a really important criteria? And in fact, it is used in like insurance companies that age, they discriminate against you if you're younger or older, or if you're a female driver versus a male driver, that's discriminated. Or if you go to rent a car, you have to be at least 25 or you get a higher rate. So what I wondered is, does your research offer an opportunity to get rid of some of these institutional allowed biases by being able to show that really there's a more root fundamental idea that's discriminating a good driver from a bad driver or a more responsible person from not? And is there a way that this stuff, instead of sort of satisfying existing policy, could push back and maybe improve policy that we already have?
Right. So I think that's kind of the key idea in some sense, that, like you said, there's this inherent trade-off, which is that's the kind of key in our framework, which is, you know, you want to lose information about that variable, but doing so may hurt your classification ability, right? So it is this inherent trade-off if that variable is a key component in making the decision. But as you say, that can often be there for historical accident or whatever reason it's there, and as something that the vendor could use or society uses because they think it's something that's correlated. But this allows the system to learn a good function that removes that information. So it turns out that in many cases we thought that variable was going to be really important, but it was a very small loss in accuracy, and we were still able to get a big gain in removing discrimination.
Can I have a follow-up question?
Yeah.
So what's your impression as to whether that loss of accuracy is in fact inherent, or whether it could be eventually compensated for, especially with additional, more enlightened training data?
Yeah. So I would agree in the sense that, well, you can always add more data or more features of the data, either dimension, more people or more dimensions of representing a person, and improve your accuracy typically. But there are cases where it will be fundamentally correlated, and so you are going to lose information. And I think there's a distinction. In some cases, there is that relationship, whether, the age of the person may be a key role in whether they have to be hospitalized or not, right? So there may be that strong correlation that exists, and removing information about age is going to decrease your accuracy no matter what you do. But as you said, if you add a lot more information, then you can still get accuracy to a high enough level. And I think that's where it comes back to society and what extent regulators want to say, okay, that loss in accuracy is palatable because we're gaining this, anti-discrimination.
Sorry. Oh, sorry. Yeah, okay. I mean, it's related, so if I could maybe hook on. So I was very curious about how you got to Z, because it seems that, in a sense, what you're proposing is a mechanism for deciding how people should be represented. And it also means that how being a minority should be represented, which is like a very political thing to do, right?
Right.
And so my question was, how do we decide what counts as a minority should be suppressed in a database to give us an equal representation? That's a really hard question.
Yeah.
And in that sense, do you think sometimes we should be thinking of different not stick to one discrimination model, but think about sometimes equal treatment, but sometimes equal opportunity, which is like on some level different, and maybe how do we get to decide what kind of representation is a fair representation of a minority? And I was a little worried about the objective to achieve an unbiased result, because bias is biased as well, right? Like, in the sense that we think that we might have a neutral algorithm for a search, but what's relevant to somebody is a very biased, or actually a very subjective thing. So who decides, for example, that a database provides a good representation of minorities or good protection? Is it, I think, a very political and subjective thing. So what does it mean to try to get an unbiased machine learning is, I think, an interesting question.
Okay, that was a mouthful.
I know,
A lot
it was
of
a bit
questions
hard
in
to
there.
put into a question. I hope it
Right.
makes sense. Sorry.
So let me
Yeah.
add a couple points that came to mind when you were saying that. So one point is that I'll start with the end, about there being bias. I think, so saying that we're trying to get rid of bias is really, it's bias with respect to exactly what we've defined. Let's say saying we're going to get rid of any ability to represent whether a person is in this particular minority group or not. Okay, so that's all that we're saying that we're removing. So it's trying to be explicit about how we're being unbiased. It's not unbiased in lots of other ways. It's
Right.
unbiased just with respect to that dimension. And then I think your beginning was getting at the fact that this is a fairly simple model where we're saying, okay, we have one sensitive variable like age or gender or something.
Right.
And obviously it's much more complicated than that.
Right.
And that's more kind of, this is an illustration of a framework, and then it's kind of putting the onus back on society and public policy. What do we want really to be unbiased? How do we want to, what kind of things do we not want to discriminate against?
Right.
And that's not, that's a
It's not
discussion that has to go on with a bigger group.
Okay. We really have time only for one question, and make this question short also.
So since Butler had to leave, I want to push back on the panel's response to Moshe's question, because we had looked at this privacy policy issue. It's in the privacy report I talked about last night. And the point is that right now, when people agree to things, they really don't have a clue what it is they're agreeing to, even those of us that are technologists. The idea of canned policies, the consumer report policy, is that even if you take that by default, you're way better off than you are in the absence of any policy at all. And therefore, it's not really akin to not patching. It's akin to maybe it's not exactly what you want, but you still have a level of protection that you don't have without it.
Yeah, and you've offloaded the problem of developing the expertise very appropriately. Yeah.
Okay, so please help me thank the panel for a very exciting talk.